So, hello everyone, thanks for coming to this talk. It's a pretty full room, happy to see that. My name is Christopher. I'm going to talk to you about running Linux at EL2. What you thought couldn't happen. So, this talk is going to be a pretty technical talk. I'm going to assume some familiarity with operating systems in general and the ARM architecture. That being said, make it interactive. I like that. Ask me questions, raise your hands, tell me when stuff's going too fast, my slides don't make sense, we'll talk over it. So, the ARM hardware support for virtualization is designed around a separate privilege level, or exception level, called EL2. So it works by extending the normal user and kernel modes, EL0 and EL1, with an additional mode, EL2, also known as hype mode, which is strictly more privileged, and it's designed to run hypervisors. And it works something like this. You run a hypervisor in EL2, you run multiple VMs in EL0 and EL1, and that's great. This works really well on type 1 hypervisors, such as Zen. You run Zen in EL2, you run VMs on top in EL1 and EL0, and everybody's happy. For things like KVM, it doesn't work quite so well because KVM's design doesn't really map so well to the ARM architecture. The reason is that Linux is designed to run in EL1 and runs in EL1, but you need the features of EL2 to run virtual machines. So we had to kind of shoehorn KVM into running on the ARM architecture in EL2 and EL1. So most of Linux runs in EL1, KVM also runs in EL1, parts of KVM runs down into EL2. So what kind of consequences does that have? Well, if you're running in a VM and you exit from the VM to the host to service the VM for some reason, it looks something like this. You have an exception from the VM kernel into EL2 to the host. Now you're going to want to run up to EL1 in the Linux kernel to benefit from functionality existing in the Linux kernel. So those two kernel modes, they share the same CPU mode and the same register state. So you have to switch that state to memory in EL2. Now you can return into Linux, do whatever you need to do. Eventually you want to come back, you do a hypercall back into EL2, switch the same state around again, and then return back into your VM. So all this state switching is kind of expensive. So what I propose is to improve on this and say, okay, let's just move all of the kernel in Linux and KVM down in EL2, not run anything in EL1 on the host, and let the VM use EL1. So a note about VHE. So VHE, the virtualization host extensions, is actually ARM v8.1 architecture support for doing exactly that without really modifying the Linux kernel. And that's great. And it's a really good starting point for doing this work. So thanks to Mark for providing the patches and making my life easier. So the meat of this talk is going to be about the implementation and how we actually go about doing this. So there are 4 key areas that you have to think about when you want to run Linux in EL2. So system registers, you have to deal with those. Memory, a big issue. Exceptions. And finally, you have to do a little bit of touching of KVM. So system register accesses. So basically, you have a lot of places in the kernel that touches a system register. And it'll touch the EL1 system register because it's designed to run in EL1. And the EL1 system registers are the ones that control the mode of operation if you're running in EL1. So now we run in EL2, so basically the straightforward approach, scatter some if-defs around there and touch an EL2 register instead. So that's fairly simple. If this ever gets near upstream, we probably have to think about nicer ways of doing that. Memory. Okay, more fun. So typical EL1 VA space, assuming 39 bits, looks something like this. You have 2 page table-based registers. You run user space in your lower half of the VA space, kernel space in the upper half, using TTBR1 EL1, user space uses TTBR0 EL1. In EL2, you, still assuming a 39-bit VA space, you have 1 page table-based register. You have 1 region. So where do you put user space and where do you put the kernel, and how does this work? So there are 2 options. Option 1 looks a little bit and feels a little bit like good old-fashioned 32-bit. You split the address space into 2 halves. So there are some problems with this approach. There are issues with page table formats. the architecture have different requirements for how page table format descriptors should be, or page table descriptors should be for when being used from EL2 versus from EL1 and EL0. This approach is going to require us to invalidate the TLB a whole lot more often. You're going to see why. And finally, well, you compress the address space available because you split it in half. So with 48 bits, that might not be a huge issue, but still. So those page tables. Okay, I apologize about the color on the projector here. That's hard to read. But basically, you want to share your page tables between kernel and user space when you do this. If you didn't, if you had separate page tables for kernel, for everything that happens in the kernel, and for everything that happens in user space, it's going to be really hard because you need to access user space from the kernel. So you need to replicate the mappings of the user space page table in the kernel page table and maintain a kernel page table for each process. And that's going to be a synchronization nightmare to maintain two up-to-date versions of the page table all the time. So that's a bad idea. So we want the same page table. Plus it would touch core code all over the place, and I have to talk to people I don't want to talk to and stuff like that. So if we look at the specific bits for the descriptors that are problematic, so the AP1 bit is basically the one in the normal world of EL1 and EL0 that controls whether user space can access either read or read and write memory. So that's fine, but in EL2 that bit becomes reserved as 1. I'll talk more about what that technically means later. The UXN-XN bit, that's a bit in the page table where if you do a memory access from EL1 or EL0, then that means user space cannot execute code if that bit is set. If you do a memory access from EL2, it means that EL2 cannot execute such a mapping. So it's basically reversed. In EL1, EL0, you have an extra bit for the opposite case, for privileged execute never. So that is, if your CPU is in a privileged mode, then you cannot execute code in that mapping. That is simply ignored as reserved of 0 in EL2. So how do we deal with that when we want the same page table, right? So we deal with it like this. So this is a slightly complicated table. It's a little bit difficult to take it all in at once. So I'm going to go through it more or less step by step. But you can refer to this as sort of, this is the solution. This is how the bits end up being set. So what this shows is for user entries up there, these are mappings of user space memory, right? And we set the bits like this, and then it's, by user colon, I mean this is the effectual permissions from user space and kernel space. Well, when you're in user mode or kernel mode. So let's look at the AP1 bit, which is reserved as 1, which is the first thing to discuss. So by examples, let's see. If the CPU is in EL0, so the CPU mode is EL0, and you make a memory access to a user space mapping, we set the AP1 bit to 1, so user space can access its own memory. That makes good sense, right? Conversely, if you are in user mode and you access memory belonging to the kernel, we have to set the AP1 bit to 0. We have to prevent user space from accessing the kernel's memory. Protection, right? What happens when the CPU runs in EL2, right? Normally, if you're in the kernel, it runs in EL1, but now we run in EL2. That's what this whole talk is about. So user memory, the AP bit sets are the same between the two tables. It's just the CPU mode that changes between these two tables. So the AP1 bit still set to 1 for user mode. That's just fine, no problem there. So if you access user memory from within the kernel, you can access it as you should, and the AP1 bit doesn't violate the architecture or doesn't do anything bad. However, for the kernel mappings, right, the AP1 bit doesn't affect the permissions of EL2 accesses, but it has to remain 0 from the requirement up there because we still want to maintain protection. So the problem is simply, we do have access as we should, but we set a bit to 0 where the architecture says it should be reserved 1. So what does that really mean? Well, reserved 1 for an RMV 8.0 implementation really means that if it must be reads as written and it mustn't affect the CPU behavior. So if an implementation is architecturally compliant, this won't mess up the CPU. Newer hardware, things could change, so don't do this on newer hardware if that changes, I guess, is the best I can say. There were two more things to notice with this setup. First, the UXN bit fun, basically the effect of this, which is different from running the kernel in EL1, is that if a user mapping is executable, it's also executable by the kernel. So that's a security protection feature which we're relaxing a little bit. So, second issue, user mode can actually execute kernel instructions now. It can't read or write anything from kernel mappings, but it can execute them. And that's kind of funny. I don't really know how it works. I haven't tried it. But what it tells me is that it's sort of the equivalent as loading a Linux image off the disk and just jumping to somewhere in it. You won't be able to do any real damage, but you may be able to get a little bit of information about how the kernel is laid out, stuff like that. So I don't think this is a huge security leak, but it's not more secure. Let's put it that way. Okay, so I said something about TLB invalidations. So let's see how that works. So let me just do a basic example of accesses to user space memory from the kernel. And I'm going to show you a TLB, a conceptual TLB, and build that up on the lower left side. So you're in the kernel, in EL1, the normal world. Right? You access something belonging to a process at some virtual address, and that entry gets filled in the TLB. It's done by EL1. It's tagged with an address space identifier, the ACID, and the entry in the TLB translates a virtual address to a physical address. You do a second address to a different process from EL1, from the kernel, to that same virtual address, tagged with a different address space identifier. It becomes a second entry in the TLB at, translating to a different physical address. Now, I changed the kernel execution mode to EL2. We do it again. Okay, we access some memory at an address in EL2. EL2 accesses are not tagged with ACIDs, right? So puts an entry in there. Now, you context switch, you access some other user space memory from the kernel. Same address. Oop, it hits in the TLB. So this is bad. So what's the solution? Well, whenever you do a context switch, you flush the kernel TLB entry, so you flush all the EL2 TLB whenever you do a context switch. So this doesn't really affect TLB performance of code running in user space, but it will affect the kernel's performance overall. So there's another option to this entire memory thing, and that is just use the entire VA space for kernel mappings when you're in kernel space. Don't have user space mapped in at all. This is slightly controversial compared to how all other architectures work in Linux. You use TTBR0 EL1, the normal EL0 EL1 translation regime for mapping all of user space. So you also get rid of address space compression. And this solves a whole TLB invalidation problem. But it doesn't come for free. Now when you're running in the kernel, you only have the left-hand side. So what do you do when you want to access user space? Think about copy from user, copy to user, clear in user, all those fun functions. So that's going to end up looking something like this. Don't try to read this code. It's just conceptual. It just shows you sort of the complexity level, and this is a very simplified version. Steve, stop. So basically what you're going to have to do is you're going to have to, in a loop, on a page-by-page basis, you're going to have to do get user pages, which walks the user space page tables in software, step by step, grabbing all the necessary logs, all that fun, and resolve the virtual address that you want to access belonging to user space to a physical address, to a page, map that page into the kernel address space, which on ARM64, it's already there as part of the linear mapping. Access it via the linear mapping, unmap the page, put your page references and all that stuff. So in real life, this code gets very, very messy. You also have things to think about, like, what happens if people call, copy to user, copy from user from in an atomic context. What do you do then?
I thought there's a A2S system instruction you can use.
Hold on. So you can potentially improve on this because this thing is really, really slow.
Yeah.
So I've actually implemented it because I started out this way because I looked at the architecture manual. I said, okay, reserved as 1, I can't put a 0 there, so that doesn't work at all. But then, I was corrected a little bit, so that actually works. But, you saw the downsides of the other thing. So this is still on the table. But booting a system with this is noticeably slow. It sucks. So you can potentially improve by using the architecture's address translation function, or instruction, which is an instruction where you basically give it a virtual address and you say, do the MMU translation from virtual address to physical address and do it in this translation regime. So that's what I sort of implemented over there in the user VA to fizz function pseudocode thing. Don't start telling me I need more ISPs and stuff. I know. It's just conceptual. So what you're going to have to do if you want to do this implementation is something along those lines. And this hasn't been completely tested through. So if people have ideas afterwards on how to actually do this and that you know the MM system great, come talk to me. But basically, you call that function. So you use the processor's built-in functionality to do the address translation. You resolve that physical address to a page. You get a reference on the page. But there's a potential race here, because right after you do that address translation, somebody else behind your back could reassign that page to somebody else, change your mappings, all sorts of fun things, just free the page, right? So if you get a reference on that page here, you have to at least do the translation again and check, does that still hold? And then maybe perhaps you can do something. And there might be a lot of race conditions that I haven't actually thought through here. So also, we don't really know the performance of the AT instruction, the consequence of putting ISBs all over. So it may not even be faster, but it's certainly worth looking into. So what I do now for my current implementation is basically go with the option 1. It has all the downsides from first, but it runs and it's relatively simple, and it's much less invasive. So the no changes to UAccess is a pretty big deal there. Okay, so that was memory.
How slower is your boot?
Sorry?
Option 1.
No, it's obviously only slower for user space. Right? Because you don't modify.
Does it slow down your boot?
Your user space boot, yes. Well, your bringing up of your init system and all that is slow, right? But it doesn't slow down your kernel boot. So the notion of why option 2 is very interesting is if you want to run VMs and you do this to run VMs faster, if you use vhost and that kind of configurations, you hardly do any device emulation in user space, then maybe it's not a big deal. Get to that.
Okay.
All right, so exceptions. Exceptions is another fun area in this case. So basically, how do exceptions work when you run a kernel in EL1? Well, if you take an exception from within running in the kernel, it's going to be taken at EL1 by the kernel, as you would want. If you want user space, you take an exception to EL1. That's the way you want it, that's the way it works, so that's good. In EL2, this is what we really want to happen. It's the same, right? We don't run anything in EL1. You take exceptions to the kernel, that's it. The question is, how do you do that? So immediately looking at it, for IRQs, it's kind of easy. You can set the IMO bit in the HCR EL2, which tells the hardware trap all RQs to EL2. So that's great. That kind of works. But synchronous exceptions, they're more fun, like a system call or page fault. What do you do there? So there's this bit in the HCR EL2 called TGE, which means trap general exceptions, and basically the semantics of that is trap all exceptions to EL2, which is exactly what we're looking for. Except what the architects had in mind when they designed that bit is, running some very simplified bare metal applications for a hypervisor without the MMU turned on in user space. So if you set this bit, stuff in user space doesn't get virtual addresses, it doesn't get the MMU, and that clearly doesn't work for Linux. So that doesn't really work. So what we do instead is we say, okay, let's build a simple page table for the upper part of the address space region, which is not used for EL0 and EL1. So we program that, we map a single page at the highest possible address, set the vbar, the vector-based address register, to that upper range, and we map in a specific little page with an EL1 exception shim in there, which just forwards the synchronous exception down to EL2. So we route exceptions via EL1 to EL2 from EL0, synchronous exceptions. So it looks like this. This is a standard vector table. And we care about the synchronous one down there, and the V entry is basically, or it is a branch instruction with some linker stuff on it. Branches to there and calls another hypercall that jumps into EL2. So it's 2 instructions, so that's not too bad. You'll notice that we also do something for our queues there. You'll find out why. So this whole approach is probably the most invasive part to sort of the main ARM64 kernel code. Requires some changes to entry.s. When you enter EL1, perhaps I should go back here, right? When you enter EL1 from EL0 as a synchronous exception, the information about that exception is going to be stored in EL1 registers. So that is basically your syndrome information and the return address to where the exception occurred from in user space in EL0. But in entry.s, that's part of the kernel. and now we change all of the kernel to run in EL2, so it doesn't access EL1 registers anymore, it accesses EL0 or EL2 registers, sorry. So what we have to do is we have to add some code to check, was this a forwarded synchronous exception from EL1 from a hypercall, and in that case, load the information you want out of EL1 registers and use that instead of the standard code path to read EL2 registers. It is what it is. So the summary of that is basically, well, it's one extra exception, it's 2 instructions, that's the cost you're going to take on the entry, not too bad, and it's a few extra assembly instructions in entry.s. So, okay, there's a little bit of a gotcha. When you do this trick with the synchronous exceptions, you have 2 instructions running in EL1, that's the forwarding part down into EL2, right? So generally when you take exceptions on a processor, you don't want to take exceptions while you're in an exception handler. You can kind of hear by the sound of that that's something you don't want to do, right? So the way that the hardware is built and the way the hardware avoids this is it sets the I bit, the p-state I bit, which masks interrupts at the CPU level, right? So you jump in your exception handler as part of a system call, you don't want to be taking physical interrupts, you want to mask those. And that works just fine normally. But you remember how we set this IMO bit in the beginning so that all interrupts came directly to EL2? Well, that bit is designed for running virtual machines, right? And when you run in virtual machines, what you're doing in EL1 is actually not processing physical interrupts, but processing virtual interrupts. So weirdly enough, that bit no longer masks physical interrupts, but masks virtual interrupts. So now you can take physical interrupts while you're running these 2 instructions in EL1. So if you're unlucky enough, a physical interrupt will come in on an instruction boundary right here, and between 2 instructions in EL1, which is kind of sucks. And that's really bad for a long chain of events can basically lead to your system dying. So what do? Simple enough. We clear the IMO bit when we return to user space. Remember, we still want to set that bit when we run the kernel because we don't want physical interrupt to jump up to la-la land in EL1 when you run in the kernel. So when you return to user space, you clear that bit. Now if there's a physical IRQ coming in while running in user space, that jumps to EL1, to our little shim, and we just do the same trick. We just forward it with a hypercall down to EL2. We set that bit again, works. So that's that. Implementation-wise on KVM, well, that was actually the most boring and trivial part. So we relied on VHG for functionality, very, very tiny tweaks. A lot of that code is based on CPU feature that says has virtualization host extensions, which gets set if that is there and enabled, which currently just checks the current CPU mode. It says, if the mode is EL2, return true. But now we have a different way of being in EL2 that doesn't, where we don't have the VHG, right? So we change that so that it checks VHG is enabled and you're in EL2. And then we introduce another one which says, it runs in EL2, which returns true if one of the 2 happens to be the case. And based on those 2, the code actually looks quite clean and clear, and they coexist quite nicely. So the final bit there is, now when we've done all this work, why did we do that in the first place? Well, it's because we can now optimize KVM to run VMs faster. So some of the things we have to do is we can essentially lazy save and restore a lot of things much more aggressively. We can move register save restore to vCPU put and vCPU load. So this facilitates going into the host kernel to service a VM quickly and going back, right? And only if you go to user space or run a different VM or do something much more invasive, then you do the save and restore dance. You can be much more aggressive on when you touch the VGIG, which we all know by now to be very, very slow. And you can do tricks with the timer as well, so you avoid saving and restoring that state. So in terms of next steps and challenges, we have to figure out, is this thing fast? I would have really loved to show you guys the performance numbers. I know I promised that in the abstract, but I simply didn't get there in time. So that'll come for the next talk. So yeah, the whole point of this is to improve performance. So if we don't measure it, then it's kind of moot.
What hardware do you run it?
Sorry?
What hardware?
Oh, so we run this on Mustang, on Seattle, on Juno, on M400 moonshots.
They have 8.1 already implemented?
No. So there was this thing about, if ndef config EL2 kernel, which is what I have right now scattered all over the kernel. Foo is the stuff that used to be there, and now I put in the bar. And this is not pretty, so I have to just look at all of it, basically, and figure out nicer ways of abstracting that and how invasive that'll be. So another interesting question, which I kind of was talking about, right? Should I even be thinking about upstream here, right? Or should I just go and forget it? It's an interesting sort of data point, but But is this something people will actually use? I don't know. So one main concern is, will this all just be dead code? Will it just be stuff that will be there, I'll play with it, but it won't get any real exposure, in which case, upstream may not be the best idea. And also, is this going to increase the maintenance burden especially for people outside the KVM area? If the general ARM64 maintainers are gonna hate this, then yeah, that's a challenge. In terms of implementation complexity, it's actually much better than I thought. I would have thought this would be along the lines of thousands of changes. This is all it takes. So that's how it looks. This is without optimizations, but I think the optimizations will go in for VHG anyway. So yeah, I mean, it's not, it's not completely ridiculous. And yeah, it works. You get this when you boot, and we can run VMs and everything. We just haven't optimized it, which is why I haven't given you numbers. So that reaches the end of my talk. So yeah, it's possible to run Linux in EL2. It's invasive, but not overly so. There are true performance benefits. Interrupt delivery latency. You would be able to probably measure something significant there. Yeah, whether we should upstream or not, I'm curious if this talk or circulating these slides will have, give me some feedback as to whether I should just forget that or keep thinking about it. So yeah, that's it. Questions? Yeah, go ahead.
When this got started, I thought you did this for because the V2H is coming down the pipe. So you are now doing this even with 8.0, you can do this.
Yes.
Right? Yeah. And what difference does the V2H make?
Well, you get another page table based register in EL2, so you don't get all the problems with memory. You can use the same descriptors as you could with EL1. And there's transparent rewriting of accesses to system registers, so you don't have to modify large parts of the kernel. And the
Is that in your patch?
Sorry?
Those changes, have you coded up?
I'm not sure I understand the question.
Making use of V2H features.
That's already in the kernel. That's, as I said in the talk, that's a foundation for this work.
Yeah. So you're saying that with your patches, you can throw it on 8.0 or 8.1, just detect it and do things.
Yeah, you can do it on hardware that doesn't have VHG. That's the whole point of the thing, yeah.
Why didn't you wait for 8.1 comes around?
It's just a different data point. And there's 8.0 server hardware out there, and I thought it was interesting to know. Published papers that said, this is the way you have to build KVM that has to jump between EL1 and EL2, and it, that has architecturally, you can discuss the value of having designed the architecture in that way. And you can say, well, okay, that's problematic because you can't modify software, and that's part of that, sort of that point. And it's interesting to attack that point and see, is that really true? Right? How bad is it to modify the kernel to run in EL2? And it's an interesting data point for people who want to say, how will this actually perform on real hardware? I think I would be interested in that if I was building a CPU.
It's also worth pointing out that this gives us a way to optimize for VHE without having VHE hardware. And I think if only for that, that's extremely useful.
Well, the counter-argument is a very complicated work that
It's 800 lines.
V2E will
700 lines. It's about a quarter of the impact of the VHE code.
Say it again?
It's a quarter of the impact of the VHE code.
Anyway.
Still scary code to read.
What, sorry?
It's still pretty complicated code to read.
Well, you haven't read the code, so I don't know how you can say that.
Takes,
So Thomas, I think we should just move on if there are other questions.
okay, fair enough.
Anything else? No? Crystal clear to everyone? Cool, Andrew. So I can bring one of you guys up here and right.
Is it, that was obviously only for ARM64. Have you tried it for ARM? Is it out of scope? Is it just that you don't have time?
I'm fairly sure those 800 lines of code don't build for ARM32. So no, I haven't thought about it. Right?
But potentially it could be done, right?
Sorry?
Potentially it could be done there too.
Yeah, absolutely. Good. Yes? You guys hand down the microphone?
It's probably a naive question. Does this impact the PSCI interactions of the kernel in EL1 today?
It's a good question. I haven't thought about it. Does PSCI make any assumptions about which mode you're calling it from?
No, it relies on whether you're using SMC or HVC to root.
Right. So if you're running hypervisors anyway, you don't run your PSCI support in EL2, so you'd have to do
run it at EL3. I mean, a good example is to look at what Zen does. Zen runs entirely at EL2 and uses
That's a good point.
PSCI.
Yeah, so if Zen works with PSCI, yes, it does. So no, it won't have any effects. Yes?
Another potentially naive question, but so this is like an attempt to run Linux and EL2 for ARM, right?
Sorry, can you repeat? I couldn't quite hear you. Yeah, it works.
So this is ARM, and you're running this at, you're trying to run the kernel at EL2, right? ARM64, of course. There are hardware sort of like assists for virtualization for other architectures as well, right? Is there some pattern of this sort that exists already for other architectures? An attempt to run Linux at the analog of EL2 for that architecture?
So I don't know. I am actually not familiar with how the hardware support for in MIPS or PowerPC or S390 or anything like that works. On x86, this is all moot because there's no difference between so on x86, the root mode is a superset of non-root mode. So there's no changes required to outside of KVM to run Linux in root mode on x86.
Okay.
But the general principle, I suppose, could apply to a hypothetical architecture that had the same limitation.
Okay, cool.
Okay, looks like we're done. Thanks.